So the first thing that we learned were our proportions. We learned how to find arc length, and we learned how to find area of a sector. You do have to memorize these proportions, but remember, they are common sense. They are part over the whole equals the part over the whole. Arc length would be like the part. Circumference would be the whole all the way around. M would be the part, like the angle right there, and 360 would be all the way around. So it's really just part over whole equals part over whole. L stands for arc length and C stands for circumference. Then we took that exact proportion and we just adjusted it for 2D instead of 1D. So for 2D, we've got area of a sector, looks like that, a piece of pie, over the area of a whole circle equals same thing, m over 360. So remember that one side of the formula is not going to change. M over 360 is going to be the same whether you're in 1D or 2D. So that's what we learned first. Okay? Next we talked about central and inscribed angles. That's what we did next. These are fundamental ones. Fundamental, like basic, really should definitely know these. Central, inscribed. Now I realize that when these are all by themselves, you're like, well, duh, Miss Tanton, this makes sense. But be careful, these are going to be hidden in a web of a big circle with all sorts of angles. So I know right now you're like, that looks way too easy, but it's when they're hidden in a web of big circles that it gets hard to find them. So how do you find them? A central angle will always have the vertex on the center. Like if that's circle E, then the vertex will be point E. An inscribed angle always has its vertex on the circle. Remember, there's another picture that looks kind of like that, and we don't call it an inscribed angle, but it has the same rule. If the arc is 100, then this angle's 50. Why is that? Because of the vertex. The vertex is on the circle. All right, so when we did our tangents lesson, we had a few theorems. One of them is the one called the ice cream cone theorem. Not called that. I just nicknamed it that. It says when two tangents originate at the same point, those tangents are the same length. And once again, when I draw this picture and they're all by themselves, it's like, oh, well, duh, those are the same length. But be careful. You have to apply that theorem even when there's something like this going on. To apply that theorem, you would need to know this one equals this one. This one equals this one, and this one is congruent to this one. Be careful because people are tempted to mark the midpoint as the point of tangency, which it's not at all. So this theorem applies to pictures even like this. Another thing we learned on the tangents day is that if I take this picture and I connect that exterior point with the center of my circle, that angle gets bisected. That was another theorem on the tangents day. So that's important. The last theorem, and you know this theorem because you've used it more often, the last theorem on tangents day was when a radius meets a tangent line, you get a right angle. When a radius meets a tangent line, you get a right angle. So make sure you're not the person on the test who does this. Don't be the person who does that on the test. Bad, wrong, don't do it. The right angle is always at the point of tangency. The right angle is at the point of tangency. It's where the radius meets the tangent line. That's where the 90-degree angle is. So please be careful about where you put that 90-degree angle. So the chords lesson was next, chords, and this one had a lot of theorems as well. One theorem in the chords lesson said, hey, if a radius is perpendicular to a chord, so if that is true, then some things happen. What happens? Well, that radius cuts the chord in half. Be careful. The chord does not cut the radius in half. The radius cuts the chord in half. The radius bisects the chord if they're perpendicular. It does another thing. It also bisects the arcs. So those arcs are the same measure, like 20 degrees, 20 degrees. Another theorem we learned that day is chords that are equidistant from the center are congruent. So if this one's 3 inches away and this one's 3 inches away, then this chord is congruent to this chord. So chords that are equidistant from the center are congruent. The last theorem that we learned that day was congruent chords intercept congruent arcs. So if those two chords are the same length, then that means the arcs that they intercept are the same, are congruent. So that arc is congruent to that arc. You don't really put tick marks on arcs, so I'm just doing that to emphasize that they're congruent. Okay, so those 3 theorems. Okay, so that was our chords day. Then we talked about those 7 angles, remember? Well, I've already talked about central and inscribed. Let me just remind you of the other 2. When an angle is inside the circle and it is not the central angle, then you add the arcs and divide by 2. You add the arcs that it intercepts and you divide by 2. If that angle happens to be outside the circle, then you do the opposite of adding. You subtract the arcs and divide by 2, making sure that you're subtracting the smaller from the larger, because you don't have a negative answer. Okay, so the last thing we learned, 3 situations. You had a nice long quiz on this. This should be fresh on your memory. So when you've got 2 chords intersecting, we're not talking about angles anymore. We're now talking about lengths of segments. The part times the part will equal the part times the part of the other chord. When you've got 2 secants involved, A, B, C, D, you do the whole times the external, and that equals the whole times the external. And then finally you could have a secant meeting with a tangent, and in that case you do tangent squared equals whole times external. So that's literally every theorem that you could come upon. So what I would recommend on the assessment is you kind of try to do all of one type of angle first. Like on the assessment, I would find all the arcs, and then I would find all the central angles, and then I would find all the inscribed angles, and that's how the assessment's going to be laid out. This isn't quite the same because they didn't give us any arcs to start with. So on a problem like this, I would probably just grab an angle and just really start domino affecting everything I can do with that angle. For example, in this cluster of 4, when you know one angle, you know all 4 of those angles. And it is delaying. Alright, sorry. So what I was saying is when you know one angle, you know all of them, because we've got vertical angles, and then we, of course, have a linear pair right there. So those are done. Now I need to work with the only other angle that they gave me, and that was 60. And you always ask yourself, okay, what type of angle is that? Okay, that's an inscribed angle. I know inscribed angles are half of their intercepted arc. So I'd find the arc that goes with 60, which is CB. I would take 60 and I would double it. So that arc is 120. This is going to domino effect. I need to find other angles that are opening up to 120. Look at angle 8. Angle 8, where is angle 8's vertex? Oh, it's on the circle. So we treat it like an inscribed angle. So you take 120 and you divide by 2. 60. Where do we want to go from here? We know AB is a diameter. You have to use diameters to your advantage. If AB is a diameter, then arc CA is 180 minus 120. So that arc is 60. Do we have any angles opening up to that arc? It doesn't look like it. Not angle 1 or angle 13. So from here we have a few options that we can do. Do you see this 60 and this 120? We can find that arc right there. Take a look, let's not go that route. Take a look at angle 5. You follow it and see where it opens up. Angle 5 opens up to 120, so that's another 60-degree angle. So now we need to find the other two arcs, because without the other two arcs, we're kind of stuck. I would actually use the 95 and the 120. So I would add my arcs and divide by 2 to get my middle angle. So I'm looking for this arc right here. So I added 120 plus x divided by 2, and that gets me 95, because 95 is opening up to 120, and it's opening up to that missing angle. So if I did 95 times 2, and then I did subtracted it from 120, 95 times 2, 190, 190 minus 120, so now I know that that is a 70-degree arc. Now that I know that that's 70, I know this one, it's 110 because of the diameter. And now I am pretty much in good shape. Let's take one angle at a time. Angle 10. What arc is it opening up to? You follow it with your fingers, follow it, follow it, follow it. It's opening up to 60. So I take 60 and I divide it by 2. Angle 11. Follow it, follow it, follow it. What is it opening up to? It's opening up to 70. 70 divided by 2 is 35. Angle 9, what is it opening up to? 110. 110 divided by 2, 55. Angle 4, what is it opening up to? Well, it's opening up to 60 and 70. So it's opening up to 130. So we would need to take 130 and divide it by 2 to find angle 4, which is 65. Angle 7. Follow it, follow it, follow it. Angle 7 is opening up to 110, so it is 55. Angle 13 is going to be the same as angle 4. They're opening up to the same arc. Look at 13 and look at 4. So angle 13 is 65. What about angle 1? Angle 1 is opening up to 70. So you would take 70 and divide by 2. And keep in mind that if you do get stuck, you can always use triangles as well. A triangle has 180 degrees, so if you know 2 of the angles, you can find the third one. All right.